Okay, thank you. So there are a few more co-authors of this presentation. So it is an idea that we are discussing in the AI for Soil Health project to have ponding time as a soil health indicator. More specific absence of ponding time as an indicator for good soil health. What we mean with that, in a healthy soil, we have large pores, we have structural pores, and it can drain a lot without having ponding, without having collection of water at the soil surface. So we present here mainly focus a bit on the modeling of aspects. With Annett, we also discussed the measurement, but as we will show, this is quite tricky. But the idea is at the pan-European scale that we can make modeling of ponding occurs or not, and we are collecting experimental observation evidence. So I'm clicking the wrong way. Okay. So what ponding time means, but the laser is not working, you told me. So you see here at the left, you see the curve, you have the time on the x-axis, on the y, we have the typical infiltration capacity of the soil. What is shown here for the blue curve, when we have a soil without compaction, with structural pores, the infiltration capacity is higher than, for example, a certain rainfall rate here of 30 millimeters per day. So there will be no ponding that will occur. In contrast, when we have compaction shown by the red line, at some point the infiltration rate becomes larger. The rainfall rate becomes larger than the infiltration capacity, and then we have ponding when the area is flat, or we have runoff and erosion when we are in steeper slopes. So we can compute this infiltration capacity is a relatively simple property of the saltwater retention curve and of the hydraulic conductivity curve. So we have two terms. One is related to the capillary properties, to capillary flow, and we have another term that is controlled by the saturated conductivity of the soil. So this is quite easy to compute. We can express this analytically when we know the hydraulic properties of the soil. So show you a bit on what this depends, I show you here very old measurements conducted more than 50 years ago. So in this first plot for a loamy soil, so you have different irrigation rates, and then you are measuring how much of this water can infiltrate and how much is running off. So this is for a loamy soil, and you see quite quickly after 10-15 minutes, not all water can infiltrate and the runoff starts to occur. When you compare this with the sand has a much higher saturated hydraulic conductivity, and there is almost no ponding. Just look here a bit at this irrigation. These are huge. They are much higher than a typical natural rainfall event. So we have about 400 centimeters per day. This is quite a heavy rainfall that you don't find very often. So one very important effect is how high is the saturated conductivity that is typically high in more coarse textured soil. Another aspect that is important to see, again, now for a loamy soil, and these are different experiments conducted with different initial conditions. So the red curve, this is a dry soil. A dry soil has a higher infiltration capacity because you have stronger capillary forces, you have more capillary flow. So this, if you have ponding or not, depends here on the texture, but it also depends on the initial condition of the soil. Okay, and so this idea to determine what are hydraulic properties when we want to use this to estimate at a pan-European scale if you have ponding or not. So what we have to estimate the soil hydraulic properties based on basic soil information that we have here for the sand and clay content, bath density, soil organic content. All the calculations we present here, they are done with a resolution of 1 kilometer, but we are ready also to bring this to this 30-meter resolution that Tom Hengley provided us the data with. So this approach to estimate hydraulic properties, this is just dependent on the resolution of the basic soil information we have. Okay, so when we have this information, this is with quite good quality, we have to compute then the soil hydraulic properties. And there is a huge zoo of rules that we can apply to the soil hydraulic properties. There are very different rules that we can use to say what are the different hydraulic properties we can to compute. I am using here an approach by Wageningen et al. Because this rule to compute soil hydraulic properties has the benefit that we can predict what is the saturated conductivity of the matrix. So to ignore the soil structures, just to predict what is the soil hydraulic property, what is the saturated conductivity from water flow we can have when there are no structural pores. Due to that, so all the figures that I show you now, the next 3 slides, this is just assuming we only have a soil matrix, we don't have soil structure. Okay, so when we can compute the soil hydraulic properties, we can estimate what is the water retention, we can estimate the water flow on the saturated and unsaturated conditions. And now based on that, we can also compute this sorptivity. This is an integral measure for how much the soil can sucking in the water. And we can compute what is shown at the right for a rainfall rate of 25 millimeters per day, where do we have ponding is occurring. So everywhere on Europe, you know, it's pan-European map, when the rainfall rate is larger than the saturated conductivity, we have ponding. The darker, the red color means the earlier the ponding begins. So only after a very few minutes, we have already ponding, then it will show here in dark red. So a map is here with the reddish map is quite clear. Where the saturated conductivity is limiting, we have ponding, this is shown in red. So the question is a bit what we do with the black color. In the black color, for this case here, there would be no ponding. And just to express now sort of a risk of ponding, what we are doing, we compute how much can we compact the soil until we reduce the saturated conductivity so much that we have ponding. So red color means we have ponding in the actual situation. Blue is a measure how much we can compact the soil surface until we have ponding. And so based on that, combining these reddish areas and blue areas, we can make sort of a risk map that shows us on the pan-European scale how susceptible a soil, a certain pixel is regarding the occurrence of ponding. Okay, so this is the situation now for one case. We have no soil structures. We have initial state at field capacity, and we have a rainfall rate of 25 millimeters per day. What is changing now when we have a wet initial state? So the soil is already quite wet, and now we have this rainfall of 25 millimeters per day. And you see here this, the capillary flow capacity is reduced. So the soil can suck in less water. And then we have what is shown here at the right, we have darker red. So the ponding is occurring earlier. The ratio between the black and the reddish area is still the same because the saturated conductivity has not changed. It just changed the initial conditions. But because it is wet, where we have a risk of ponding, ponding will occur earlier. Now the second case, now we increase the rainfall rate from 25 millimeters per day to 50 millimeters per day. And you see for the heavy rainfall events, we have now a lot of red area, only a few, and the black area where we have no ponding, it is much smaller. So based on this idea, then when there are no soil structures, when the flow processes are just controlled by the soil matrix, quite a lot of the pan-European scale is susceptible to ponding. Okay, luckily, and also for this project, we have soil structures, we have larger pores that can change the entire picture. The question is a bit, how do we quantify the existence and the properties of the soil structure? What is shown at the top is the hydraulic conductivity as a function of the matrix of the water potential. And you see this bump highlighted with this blue dashed line. So the blue dashed line means when we only have matrix, and then when we have structural pores, we can have a much higher saturated conductivity. So this contrast between saturated conductivity with structures compared to conductivity with only with water-filled matrix, this can be quite high. And this can express, for example, as a function of the leaf area index, as shown here by a work of Sarah Bonnet. There are different rules that can predict what is this ratio between structural conductivity compared to matrix conductivity as a function of leaf area index, as a function of biomass. And we hope that also in this project, AI for Soil Health, we find new ways to predict what is the structural effects of the saturated conductivity. Okay, as I mentioned here, I'm using now to estimate this effect, I'm using this reddish curve. Then we are using the leaf area index, and based on that we can predict the saturated conductivity. And you see now it becomes much more, we have a higher saturated conductivity. This has a huge presence of structures. effect of the saturated conductivity, and accordingly as well on the ponding. On top, you see here again this reddish blue map for a rainfall event of 50 millimeters per day. And now when we add the structures, you see that the picture switch from reddish to bluish. And so this has the presence of structure has a huge effect of saturated conductivity and accordingly on the ponding time. So we think modeling-wise, I think we have quite a good understanding how to see how sensitive the ponding time is to the soil hydraulic properties. And I think we also have quite a good idea how we can compute and predict the hydraulic properties of the soil with or without structures. Modeling-wise, I think we are on the good side. From a measurement point of view, I think it's quite tricky, and that's the reason that we are collaborating with the Planet group, with Annett, to see a bit, to deduce the most scientific and best information to detect this ponding. So far, what I present you now, this is what we have done with publicly available data, not yet with the best possible information. So we are using Sentinel-1 in the C-band, and we are with 2 different polarizations, with backscattering information with a resolution of about, I think, 30 meters. And we try to, can we observe some ponding in some areas? We are looking now and collecting a lot of observation of ponding, but because we are not yet that far in that sense, I'm just collecting data in front of my house, so to speak, where I'm living along a railway track. So on my daily journey from when I go to Zurich, so I just make some pictures to see, when do we have ponding after a heavy rainfall event. So I do this here along a railway track. This is for one heavy rainfall event with 50 millimeters per day. And then I also, as a function of time, I collect a bit at some sensitive spots. Is there ponding occurring or not? And so what we just started, and what we do is together with Planet to see a bit where are good training sites, which has a good information where we can deduce some ponding out of it. What is shown here in the figure, first at the left, this is the rainfall rate in blue, then the vertical polarization shown in red, and you see there that when the rainfall occurred, when ponding occurred, you have this drop in this in the backscattering signature. That and when the ponding was gone, the signature went back. So this is an indication that probably we are really measuring the ponding with this C-band signal. Then what we see at the right, you have a 2 plot. On one hand, on the x-axis the vertical backscattering polarization, and on the y-axis the ratio. And there we have the point where the ponding occurs is also quite nicely marked. The same is true for this other side here where we have observed ponding. And you see here in this diagram, the 2 days with ponding, they are very clearly marked. So maybe there is a lot of noise in it, and this is of course not the proof, but for me at least it's sort of a hope that it's worth it to dig in deeper to see with which remote sensing signature and with method we can detect this occurrence of ponding. Okay, so to conclude, this ponding time, when the rainfall rate is higher than the infiltration capacity, then we can have ponding or runoff. We are referring here only to the case of infiltration excess. So when the hydraulic properties are not fast enough, I'm not talking here about the saturation excess where it's just raining so much that the soil becomes full. So this is really a soil surface property. So the risk of ponding, we can model this at the pan-European scale. We have quite a good idea how to do it. This risk of ponding is not a constant with time. It will change with climate change because we will have different precipitation pattern. This can have effect on ponding as well. And the remote sensing problem, this is a problem we are working on. We hope a bit that when we collect many data for different sites under different conditions where ponding can occur, that when we combine different remote sensing methods, that it's also possible to detect this by remote sensing. Thank you for your attention.